All right, part two of your notes. We're still on the front side. We're going to check assumptions for this problem that I gave you. So part two here, I'm thinking I'm getting better at this screen recording thing. One thing that I know for sure is not getting better is my handwriting, but, well, you guys know that, right? All right, so I'm going to read this first problem out loud. An educator believes that new reading activities for elementary school children will improve reading comprehension scores. She randomly assigns third graders to an 8-week program in which some will use these activities and others will experience traditional teaching methods. At the end of this experiment, both groups will take a reading comprehension exam. Their scores are shown in the back-to-back stem and leaf block. These results suggest the new activities are better. So, clarifying this up a little bit, we have two groups here. We have two samples. On the left, we have a group of students, and on the right, we have a group of students. Let's label this one first and label this one left. So these students that have these new activities, what they're doing is they're trying something out. They're trying these new methods and activities, and they want to see if their scores actually go up with these new methods and activities. The control group, these are the ones that are actually doing traditional teaching methods. So if you remember with the stem and leaf plot, this is just a way to kind of show data. So for example, this control group on the right side, I took this part 1, which is 0, this actually represents a 10. And the one with the 7 represents a 17. So we have two different sets of data here. So here we have 10, we have 17, we have 20, 26, and so on. Right on the left side over here, you would have a 24. So be careful with that first one. It's very easy to kind of think that that says 42, but the stem is actually in the middle there, so it is 24. All right, so what we're going to do is we're actually going to do both a confidence interval and a hypothesis test on the back side of this. But before we can even get to that, we always have to check our assumptions and conditions. So let's do that first. Keep in mind here, we have two samples. So checking randomness, most of the time this is going to be right in the paragraph. So I believe in this paragraph, I'm looking for it, yep, right here. He randomly assigns third graders to, let's see, to one program, and then she randomly assigns them to the other program. So students are randomly assigned. Independence is our next check. Now, something to mention with two samples. If you remember, we did this with two proportions. There's actually two independence checks. 10% rule is usually the one we do with independence, but when we have two samples, we also want to make sure that those two samples are independent from one another. So in other words, one sample does not affect the other one. So in this case, a student's score and the new activities should not affect a different student's score in the control group. So here we can say a student score from one group and so So a student's score from one group won't affect the other group. So that's one independence check, but there is that second independence check, and that's just the 10% condition, basically checking that both these samples are less than 10% of the population. And this you have to actually count the total numbers in each of these separate samples from up top. I know that there's 22 students in the control group. 18 students that are trying these new activities. We have to actually check that both of these satisfy the 10% condition separately. So when we do this, we can say that 18 and 22 are both less than 10% of all third graders. At the end of the day, we're trying to figure out if these new activities actually help these third graders improve their reading score. Alright, so we have random, we have independence, and you guys remember that last one, normality. So let me erase these assumptions, and we'll get normality. So with normality, that's where we have the large counts condition. Basically, is our sample big enough? Do we have at least 30? Well, in this case, we don't have that. Now, if you guys remember, I told you guys that it's okay if our sample isn't at least 30, as long as it follows somewhat of a normal curve. So if it's unimodal and symmetric. So if you look at the stem and leaf flat, what's actually nice about a stem and leaf flat is it actually shows you the distribution of the data. And I can do that by just drawing a curve right over the data. If I do that, you can see that both these distributions are actually unimodal and roughly symmetric. So we can actually say that both of these samples are somewhat normal because they are both unimodal and symmetric. Alright, so our assumptions and conditions are met. Before we start the next section, I would advise you to now pick up your calculator, and what you should do is enter this data as L1. So remember, that data is actually going to start out with the numbers 24, 33, 49, and so on. And then what you actually want to do is enter the other set of data, so your control group. So go ahead and take a couple minutes and do that, and then when you finish this, go ahead and proceed to part 3 of our note.